Lesson 3, the Web Layer, Understanding REST and Controllers. 1. Introduction. Good morning, afternoon everyone. Thank you for joining today's session. Our objective is to explore how we move from a simple application setup into implementing a full CRUD, create, read, update, delete, style REST API using a modern framework. This marks an evolution from merely returning a static or fixed message to managing dynamic entities in memory, offering a foundation for future persistence layers. 2. Context and rationale. In the previous lesson, we had a basic Hello World style application. While that is useful for illustrating how the framework works at a minimal level, it does not reflect common real-world requirements. What many applications need is the ability to handle collections of entities, to create new items, to retrieve one or many items, and to manage their lifecycle. The focus of this lesson is to implement a task management API in memory. Even though we are not using a database yet, this approach helps us focus on the web layer, data models, and the HTTP interface without introducing complexity of persistence or transactions. 3. Data model design. We begin by defining a simple data structure to represent our domain object, task. This task has 3 basic attributes: an identifier, a description, and a completed flag. Because we are operating in memory, we will explicitly handle identifier generation and storage. The design aims to keep the object immutable, or at least conceptually immutable, to simplify reasoning and reduce side effects. By focusing on a minimal model, we can concentrate on how we expose that model over HTTP, how we map requests to operations, and how we return well-formed responses. 4. Controller and in-memory storage. The next step is creating the API surface. We introduce a controller which will expose multiple endpoints: one to retrieve all tasks, one to create a new task, one to fetch by identifier, and potentially endpoints for update or deletion, depending on how far the lesson takes us. Internally, the controller manages a simple list, or equivalent collection, of task entities and a counter to generate unique identifiers. This in-memory collection serves as our data store, temporarily. The choice of an in-memory list highlights that this is a learning exercise, not production storage, yet allows all CRUD operations to be performed and tested. 5. Endpoints and HTTP semantics. We expose an endpoint for retrieving all tasks. It returns the collection of tasks that exists at that moment. We expose another for creating a new task. The client submits a task representation, without an ID, and the server assigns a new ID, adds the task to the list, and returns the created task along with the proper HTTP status code. We also provide an endpoint for retrieving a task by its identifier. The client supplies the ID in the path, the controller locates the matching task, and returns it, or handles the case where it does not exist. The lesson also touches on HTTP status codes, for example using the created status when a new resource is created. This emphasis on HTTP semantics is important. Building APIs is not just about working methods, but about adhering to conventions that make them understandable, interoperable, and predictable. 6. Testing and verification via client commands. To verify that our API behaves as expected, we use client-side commands, for example command line calls, to create a task, list all tasks, and fetch a specific task by its ID. This exercise is crucial. Beyond writing code, we must confirm that the endpoints behave correctly, that status codes are right, and that the data returned aligns with what we expect. Although we are not yet persisting to a database, the in-memory list should still reflect the correct state across calls. This step reinforces the discipline of verifying API behavior, especially helpful when later moving to a database or distributed environment. 7. Acceptance criteria. By the end of this lesson, the application must compile and run with the version constraints specified, Java 17, framework version specified, build tool version specified. The key functional acceptance criteria are: when the client sends a request to create a new task with given description and completed flag, the system successfully assigns an ID, stores the task in memory, and returns it with the expected status. When the client requests the list of tasks, the previously created tasks appear. When the client requests a specific task by ID, it is returned correctly if it exists. These criteria ensure that all necessary parts of the CRUD API are operational in this simplified environment. 8. Why this exercise matters. Why are we doing this in memory rather than immediately using a database? Because the web layer and data model design often represent the largest conceptual shift for developers new to REST frameworks. By isolating those concerns, model, controller, HTTP semantics, we build a foundation. Later, when we introduce persistence, transactions, security, and performance concerns, we will be in a position to abstract those layers away without rewriting everything. In other words, this exercise helps us decouple the API layer from infrastructure concerns, which is good design practice. 9. Looking ahead. Once this in-memory version is stable and understood, the natural next step will be integrating with a database, applying validation, handling update and delete operations, adding behavior around tasks, like due dates or priorities, implementing error handling for missing resources, and considering pagination or filtering for large collections. But those will be covered in subsequent lessons. For now, mastering the in-memory CRUD API is our goal. 10. Conclusion. We started with a simple Hello World application, and now we've built a more realistic REST API managing task entities in memory. You've seen how to design the model, how to expose endpoints with correct semantics, how to maintain state in memory, and how to test the API via client commands. This sets the stage for future enhancements.